Alrighty, y'all. Today I'm taking a look at question 4 for Recitation 10, the final question for Recitation 10, and we're going to be finding the electric potential at that point on the drawing there. So our equation for electric potential is based off of our delta U, our change in potential energy, and essentially it's just Q times delta V is going to give us our delta U. So solving this for delta V is delta U over Q, which is fine. So now we're just going to use our equation for potential energy and divide by the charge, because we don't have a charge there, so we're just canceling that bit out, right? So that's going to be our integral, negative integral of our Q electric field dotted with dr from R1 to R2, whatever. And that's all divided by that Q, so that's just going to cancel out this Q here. So our actual equation is just going to be negative integral from R1 to R2, the electric field, times dr. So this one might seem, this problem might seem pretty complicated because it has the things on both sides. We can just have our dr is going to be, our r vectors are going to be coming from here. They're going to be going this way, right? It's going to be coming from infinity. And so, because our potential be 0 at infinity, so it's going to be going infinity to this distance here, 1 centimeter away. So we can plug that in. We're going to get our integral from infinity to 1, and that's going to be of our electric field times dr vector, right? So now let's tackle this electric field. Since there's 2 points, the electric field at each given point is going to be the sum of the electric fields from each point, right? So our electric field is going to be KEQ, we'll call this Q1, this is going to be Q2, KEQ1 over this R, some distance R from wherever, between that proton and wherever we are, plus our KEQ2 over, again, it's going to be that same R, and then both of these are also going to have an R hat given that directional. I'll make that a capital R, actually, the capital R hat, the direction that it's going to be going in. So if I break these down further, we're just going to say this distance, we make this triangle over here, just looking at the proton. We have this distance, 1, and oh, this is centimeters too. I'm going to have to, so I wrote 1 down here. It's actually 0.01 because we want to stay in meters. And then this distance was our R from before, because remember that's our R vector. So that means this radial distance is going to be Pythagorean theorem, the square root of R squared plus 1 squared. Right? So that's going to be this R, this capital R that I was using over here. So that's going to give us our big R equals square root R squared plus 1 squared. There. Now, I forgot that these are both squared on the bottom here. I'm sorry. Just these in the equation for the electric field, it's KEQ1 over R squared, and times that R hat. Now we're going to find the directional vector, the directional unit vector for this R. So if we're looking again at our triangle over here, which I'm just going to move so it's not in the way, if we're going to be going 1 in the x direction and R in our y direction. So that's going to be 1I plus RJ. Both these are the j hats, right? But we have to divide by, again, that magnitude of the vector, because we're trying to make the unit vector, so that's going to be square root of R squared. We're dividing by, again, this magnitude R, which we said was square root of r squared and plus 1 over square root r squared plus 1. So this is going to be our r vector here. So now we have all of our pieces to fill in this equation. So we have our electric field. Well, we have most of our pieces because I said this was going to be positive because that's going to go in the positive x direction. But this one, it's going to be a negative x. That's the only difference between them. I'll write that out, but I forgot to mention that because I was just focusing on the proton for that one. All right, so that's going to be Ke times the charge of the proton, Q1, over, and since it's squared, we can just make it r squared plus 1, because again, since r is the square root of this, r squared is going to be r squared plus 1. And then that's going to be all times this unit vector that we said was I hat over square root of r squared plus 1 plus r j hat over square root of r squared plus 1 plus, we do the same thing for the electron, which is going to be Ke Q2 over, same r, again, same magnitude, r squared plus 1 times the same, it's going to be the same unit vector, except negative in the x direction instead. So that's going to be negative I hat over square root, I don't know why that happened, square root of r squared plus 1 plus r j hat over the square root of r squared plus 1. Now we get to simplify this monstrosity just a little bit. So since it's a proton and an electron, we know they're going to have the same magnitude charge, just opposite. So I'm just going to say that Q2 equals negative Q1. So I can plug in this negative Q1 in for Q2 here, and then that'll help simplify as well. And then for each of these unit vectors, I'm also going to be factoring out this denominator, because that's the same in all of them. So all of this now kind of factored around. This would be Ke Q1 over r squared plus 1 to the 3/2. That's going to be I hat, because this is to the 1/2, this is to the 2/2, so that's going to be, add them together to the 3/2. I hat plus r j hat, and that's over here, Ke, and we said this was negative Q1, so I'm going to put that negative here, Q1 over r squared plus 1 to the 3/2 times negative I hat plus r j hat, again, because I pulled out that denominator and made that look nicer. Now I'm going to take this negative sign, move that into here, so that I can then start combining with these as well. I'm going to keep factoring. So we're going to get this is equal to Ke, we're factoring out the Ke from each side, we're factoring out the Q1 from each side, we're factoring out the r squared plus 1 to the 3/2 from both. And now that's going to leave us with this I hat plus r j hat plus, because again this is the negative and the negative, we're going to give us a plus I hat minus r j hat. These are going to cancel. This is going to leave us with an I hat, just 2 I hat, which we can pull out the 2 again. So it gives us that finally our electric field is going to be Ke Q1 2 over r squared plus 1 to the 3/2 in the I hat direction. Now, if we look back at our original picture, this makes sense, because since we have a positive and a negative charge on here, the positive is going to have an up effect and the negative is going to have the down effect, they're going to have the equal up and down, so our j direction should cancel. But because there's the positive over here and the negative over here, we're going to just have in the positive I hat direction our net electric field. Now let's look at this dr, right? It's the only other part that we need to find, and then we can plug it back into our original equation to get that potential difference. So when we're looking at r, like I was saying earlier, this is our first r, this is our second r. Our directional is going to be like, it's going to be vertical, so it's going to be in the positive j hat direction, and it's just going to have the magnitude of r. So that's, you just come over here, dr, well, r is just going to equal r directional. It's going to equal r, just the magnitude of it, times j hat in that direction. So our dr is going to be j hat dr, right? So now if we plug all of this back into this equation here, we come over here, we're going to get the negative integral from infinity to 0.01 of ke q12 over r squared plus 1 to the 3/2 I hat dot j hat dr. Fun fact, actually, I hat and j hat are perpendicular. So if you do I hat dot j hat, it's just going to equal 0. So this entire thing, all multiplied together, just going to go to 0. That's your final answer. 0. All right, well, thank you all very much for watching. I hope this helped. Let me know if you have any more questions about this or about any other problems that you want to see worked out, and I will do my best to explain them because I guess Sydney explains stuff.